In this episode, we're finally getting serious about the Turbo K24 FRS build. After finding out that our factory rotating assembly weights are all over the place, we put our balancing jig to the test to shave off grams from our pistons and connecting rods to get them to all match up within 0.1 grams. Follow along and I'll show you my exact method that you can do at home. But before we get started, we do have to pick up a few new tools to help us with this job. Kind of crazy, everything's at Home Depot's locked up now. Alright, today we are back in the studio and we are actually going to get started on building the engine for the K24 turbo swap that's going into my FRS. Hopefully we get this car running at some point this track season. So here we have our Manly H-beam rods and we have our JE pistons that are slightly lower compression because we're going to be boosting. And yeah, we're going to be balancing these guys today, get them as close in measurement as possible to each other. So here's the thing about balancing. These products are going to be paired together from the manufacturer, but they're still going to be potentially like one of the rods or one of the pistons might be like a gram off or something like that. And depending on the type of build that you're going for, I really do think it's a good idea just to spend the extra time before you start assembling just to get these matched. It's not too complicated. There are some tools that you may need to get, but honestly they're tools that you'll probably have a use for outside of just balancing these. Whether you're building a high revving engine or something in the 6,000 to 7,000 RPM range, I think it's still worth doing the balancing because you're just gonna have a smoother running engine. And you really only have one shot at doing this before everything is cased together and bolted up. You're not gonna be opening up your engine again until it blows or retires. When you get these rods from the manufacturer, they're gonna be pretty close in weight, but they're often potentially a gram off, maybe the lightest to the heaviest. So we can see that these ones are marked 169, 170, 170, 171. So we already see that there's a 2 gram split, and 380 point something, 380.8, 381, 382.2. So there are some discrepancies in the weight here that we can see. Before we get started with any cutting and shaving whatsoever, we want to make sure that we get some factory measurements. So what I recommend is you get a digital scale down to 1/10 of a gram of resolution. And what I have here is just a coffee scale. Any food grade scale would work fine as well, or you can get something that's meant for the shop, but the most important thing is you get down to 1/10 of a gram. One other thing about scales that we need to discuss is the difference between accuracy and precision. So you might be wondering, aren't those two the same thing? Well, technically accuracy refers to how good the scale can actually hit the actual absolute weight of the item, and precision actually refers to repeatability. So if you think about hitting a bullseye, accuracy is hitting the center and precision is having a tight cluster. And when it comes to balancing the rotating assembly, the more important thing is precision, because we don't really care about the absolute weight of the item so much as opposed to how close each individual combination of parts that are assembled together are to each other. And the way that we can test the precision of a scale is to repeatedly put the same thing on and off to see if you get the exact same measurement each time. All right, so the first thing we'll do today is do the pistons because they're actually a little bit simpler to do than the rods, and we'll get into that reason why later. And one of the interesting things that you'll want to do is actually not only weigh the pistons, but we'll also want to do the wrist pins, which are in this box here, as well as the rings if you want to get really specific, although I don't think those are going to change very much. The reason why we want to do the wrist pins is that there could be a bit of a deviation given that these have a pretty high absolute weight, and if we have mismatched pistons and mismatched wrist pins, we can actually mix and match those combinations, and you might actually get to a pretty close weight balance without even doing any shaving. So in the case of that is a possibility, we're going to definitely weigh these first. So over here I've set up a spreadsheet with the item that we're weighing, which example, so A, B, C, D, because we've got 4 of them, whether it's the initial weight or modified weight, and 5 weights, and then we're going to take the average of that measurement. Now it may seem a little bit overboard, but trust me, you're going to look back and you're going to wish you took all these different measurements and written them down where it's actually easily legible. I know a lot of people use pen and paper, but especially when you're trying to get the averages of things, this is just going to be much easier, and you're always going to have a digital reference. So here are all of our wrist pin weights averages, as you can see, from the lightest at 132.4 to the heaviest at 132.6. We have 0.2 grams to play with. So now let's weigh the actual pistons themselves. So the JE pistons themselves came in within 0.1 gram of each other. Actually, 3 of them were exactly the same at 355.2 grams and one at 355.1. So awesome job, JE. I love this. And just for the heck of it, we're actually going to measure the ring sets as well. Lots of mix and matching potential here, but I honestly think they're all just going to weigh the same. So let's see. Now that we have every individual piece weighed up, we're gonna start doing some combinations. And if the math is correct on the initial measurements, they should be pretty close together as we mix and match the lighter pieces with the heavier pieces, try to get a good average. So we're gonna throw everything that would be assembled together all at once onto the scale just to get a measurement. And that way we can just start storing the pieces together as a collection. So we've done all our combinations and we're pretty close. We do need to take a couple of tenths off of a few of the pistons. We've got average weights of 511.2, 511.1, 511.1, 511.04. So I think our target weight is going to be 511.0 if we can hit it. So let's actually talk about where we can remove material from our piston. So the first rule, and it's a very simple one, any of the exterior facing the top of the piston, the skirt of the piston, we do not want to be touching any of that. So we really have just the bottom side. And the second rule is you don't actually want to touch the floor of the piston when you're looking at it from the bottom up. And this is basically the exact same reason as to why we don't want to do anything to the face of the piston. Similarly, we don't want to do anything to the floor when we're looking at it from the bottom up. So that kind of leaves us this interior part of the skirt here. Now where we typically have the most space to work with is right around these corners here where we have the hole for the wrist pin, but the way that these are forged, you have a lot of space here, a big distance between the hole and the perimeter. And so what we'll do is actually work on this corner here, and whenever we remove material, we want to make it symmetrical. So you want to balance the material move from this corner and here and here. So all 4 corners, and it's nice toward the center. So we're not going to have any imbalances there in terms of the material we remove. But it's important that when you do this, just to remove a tiny little bit at a time and remeasure and see how close you are. Now, technically it is possible to remove material from the wrist pins, but these are made of a much tougher material than the aluminum piston. So it's preferable to work with the pistons and save your effort from trying to grind these out. But if you do insist on grinding out and removing weight from the wrist pin, what you can do is just chamfer the inner lip on both sides. Just take a little bit off. Do not bore the hole on the inside, just chamfer the lip. And to get the job done, we'll be using a die grinder, and you usually want to be using a bit that's made for aluminum. This is actually one made for steel, and it'll work in a pinch, but it's probably going to get clogged a lot more easily. But since we're not removing too much material, it should be all right. Now, one thing to be mindful of is that if you're targeting within 1/10 of a gram, which we are doing here, you need to make sure to use a compressed air blaster of some sort to clean out the shavings on the inside after every single grinding session, so that that doesn't throw off the actual weight of the piece from the loose debris of aluminum shavings. And don't forget to also clean off your scale. And we're just going to do some very light sanding to deburr this and make it a little bit smoother, because the last thing we want is a tiny shaving of aluminum breaking off after we've already built the motor. After deburring the edges, I did a final weighing of the completed piston sets to confirm that we were spot on within 0.1 grams across all 4. Now that our pistons are all set, let's move on to the connecting rods. So as I said earlier, the rods are actually going to be a little bit more complicated. The main reason is that we are going to actually take 2 different weights for each rod. We're going to need to weigh the weight of the big end as well as the weight of the small end. In technical terms, the big end is actually a rotating mass along the crankshaft, and the small end where the piston is going to go is a reciprocating mass. So when we balance the big end, we're taking care of rotating mass balance, and when we're taking care of the small end, we're taking care of the reciprocating mass imbalance. Now, before we do any fancy balancing, we are going to just get the initial weight of each rod. While we're doing this, I'm actually going to take the measurements of the connecting rod bolts as well, as they can be used to balance the rod without removing any material if we get that lucky. So check this out. This is why it's important to do this, as this bolt is completely covered in oil or lubricant. We're actually going to create a material difference in weight by removing some of this excess fluid. One thing to be careful of when you're doing this is to not separate your caps from the rods, as they're actually paired and they should be matched up in the direction that they come from the box. It's not compatible to flip them the other way around. These mating surfaces are extremely precise. By removing the excess oil, we actually drop the entire weight of this rod assembly by 1/10 of a gram. So I've ranged all of the connecting rod bolts from the lightest at 26.5 grams to the heaviest at 26.7, almost 26.8. So it's a good thing we did this, because with two of the lightest to two of the heaviest of the connecting rod bolts, we could do a swing of 0.4 grams at the big end for the lightest or the heaviest connecting rod. So I actually just got finished balancing the stock weight of the rods without doing the split weight, and the lightest one came in at 496.9 grams and the heaviest came in at 500.3 grams. That's a difference of almost 3.5 grams, which is personally, I would say, like on the high end, but we don't actually have to do anything with that number just yet, because we need to first do the split weights and then take care of the total weights. And to do that, we actually do need a bit of a tool, a balancing jig, and the professional ones that you can find online are pretty expensive, so I actually decided to 3D print my own. So let's see how well it does on this job. Assembling the jig is pretty straightforward. We just put one end on an adjustable height stand and the other on a fixed stand on the scale. I'll put a link in the description below if you want to get this balancing jig. A bubble leveler should be used to make sure the centers of the two ends are at the same height. So a couple of notes on using this setup correctly. One thing I did notice is that the scale is actually pretty sensitive depending on the distance between the two ends in terms of where the supports are. And what I did is I just marked it down with tape so that I get repeatable measurements. The other thing you have to be sure of is that the rod is not touching any of the structure at all in terms of the uprights, and only touching the internal bushings. So you want to take a look on the sides, at the bottoms, on both sides. Try to get this as straight as possible and perpendicular to the scale. After our measurements, our lightest came in at 325.0 on the big end, and the heaviest was 326.6, so 1.6 grams difference. Now, before we start shaving weight, we do have to remember our connecting rod bolts, and some of these are lighter and some of these are heavier, so we're going to mix and match the lightest bolts with the heaviest big ends, take a remeasurement, and that will actually tell us how much we need to shave off of the big ends to get them to match. So we just finished our first round of measuring the big ends. After mix and matching our connecting rod bolts from ARP, we are actually able to get two of the rods to get the exact same measurement of 382.2 grams, which is great. We don't have to shave two of them on the big end. And the third one is 382.5, and the heaviest is 383.6. So that's 1.4 grams of difference in the heaviest one, fully assembled on the big end. Not ideal. We're actually gonna have to shave quite a bit of material to make that work, but let me show you exactly where you can actually take off the material so that you are not impacting the rigidity and the strength of the rod itself. Okay, so in terms of where we can and cannot remove material on the big end, the first rule is to not remove any material from the top ribs of the cap. It's very tempting to use this material. You know, it looks like it's fairly innocent to do this, but the ribs impart a lot of strength onto the rod cap, so avoid this. We also don't want to obviously touch any of the inside where it is going to make contact with where we are housing our bearings. So the ideal spot is actually going to be along the outside of where the rod bolts are going to be going. So if you see this profile here, there's a little bit of excess material that we can use to shave and round off and just give it even more of a circular radius on both sides. And similar with the piston pistons, we want to balance things out and keep things symmetrical. So we're basically going to be shaving material off of here, 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 and here. Now, because these are made of steel, you're going to not need to remove as much volume as we did with the pistons. So what I would recommend is start with your heaviest big end. That way you have the most leeway in terms of trying to figure out how much material you need to remove to hit your targets and go from there. Now, the ideal tool to use to remove material from the connecting rod big end and the small end is going to be your traditional tabletop belt sander. But I actually don't have one of those right now, and what I actually decided to get instead is this Milwaukee band file. And the reason I went with the band file is, it has the same concept of using a belt driven sander. But the thing is, if I'm only going to get one tool, I'm actually going to be able to use this later for my FRS build in removing some of the spot welds to get things out of the transmission tunnel. So a bit of a 2-for-1 here. Not the perfect tool for this job, but I think it's going to be 90% there. We just have to be a little bit more dexterous in our movements. And regardless of whether you're going to use a tabletop belt sander or this band file, you're going to want to get a ceramic set of sanding belts. This is the Cubitron from 3M, highly regarded stuff. Definitely don't want to be using aluminum oxide. It's just going to create a lot of dust and not really take off that much material from the steel. Loading up the belt is quite simple. We just have to loosen this knob, slides open, push in the file where it clicks. We slide on the fresh belt and then release the tensioner. Now, traditionally, the tool is used in this orientation to remove spot welds. What I'm going to do, because it does have 360 rotation, is orient it like this to reduce the distance between the contact point and my hand so that we can be a little bit more accurate in how we file the connecting rod. Alright, so what we're going to do is take our heaviest rod, because it'll have the most material for us to work with to kind of hone in on how much we want to remove. Slap it into a tabletop vise here. We've got some rubber grips so we don't damage the rod sides itself. And then I'll show you how we're going to remove the material using this band file. Now, what I'm also going to do here is just mark the area with Sharpie so we know which areas we've already made a pass through. You'll definitely want to mask up for this one, as the steel dust is quite fine. So I've just gone ahead and done some removal on the 2 connecting rods that needed weight removed. And we're now just gonna do a quick remeasurement of all the connecting rods just to see how close we are to each other, whether we've overshot or underdone it. We still have opportunity to make some adjustments. I think we're pretty much as close as we're gonna get on the big ends of the connecting rods. We're basically teetering between 3D2, 2, 3D2, 3, so I think the weight is basically right between the two. Now let's move on to the small end. We can use the jig to validate, but what we can do now is just shortcut and weigh the entire rod and match all 4 connecting rods to the exact same total weight, because any weight we remove, we're only gonna be doing it on the small end. And since the big ends are all balanced, we then basically know that mathematically any weight that we remove from the small end to make all 4 connecting rods weigh the same is going to actually balance the small end as well. When it comes to balancing the small end, it's pretty straightforward. We just want to focus on this main face on the exterior here. Just make smooth, light passes and let the belt do the work. One thing to be mindful of is we do not want to touch the faces here where the wrist pins are going in, as we don't want to affect the thickness of the rod in this dimension here. As you make your passes, be sure to avoid going as far down as the ribs, as we have mentioned that this will affect the structural integrity and the strength of the rod. Ideally, we want to remove an equal amount of material from along the entire small end to balance things out, and to not remove any more material from any one spot than we need to. We were able to hit our 0.1 gram target by shaving the small end and reweighing the entire assembly. If you don't trust the math, then you can also flip the jig to weigh the small end independently. The very last thing we're going to measure today is the connecting rod bearings. Technically, they are part of the big end, and we should weigh these just to make sure that there's no deviation. Now, there was some variation in the bearing halves, but we were able to make match pairs by combining the heaviest with the lightest. So there you have it, balancing the connecting rods and the pistons down to 1/10 of a gram. Now I know this is really tedious work, so just take your time with it. You can always remove more material, but you can't really put it back on. And as a quick reminder, all the tools that you need to complete this job are down in the description below. If you have any questions about the process whatsoever, don't be shy, add a question or a comment down below, and I will come back to this video and answer as many as I can. And if you've enjoyed this video, consider giving it a like or even subscribing to this channel if you want to see more content like this. And I'll see you guys on the next one.